Okay, first up from chapter 20 is number 7. This problem requires the use of a rather obscure or esoteric formula for mean free path. We're not going to use this a whole bunch, but we should look at least one problem requiring the use of this formula. Of course, it's a silly cartoon picture, but you can think about gas particles as little spheres separated by a characteristic distance. And they're all moving about because of their temperature. As long as the temperature is not zero, then classically you would think about these little spheres as moving around randomly. In the modern picture, that's kind of, it's a little naive. In fact, the closer you get these together, the more you have to think about them as waves, which is a very bizarre idea. And unfortunately, we don't have a whole lot of time this semester to talk about that. But for a moment, let's pretend that all of these are not moving with the exception of this one. So this is the one moving. And we know from Newton's first law that unless it's acted on by a force, Newton's second law, both of them really, we know that this thing should just continue along a straight line path. It's going to do that until it has an interaction or a collision with one of these other particles that will deflect it. And we use this letter lambda for the mean free path, which is on average how far one of these can go before it knocks into another particle. And it's pretty obvious that the more densely packed these are, the shorter the mean free path. So if you had this many particles packed into your volume and you look at just one of them, it's going to immediately collide with another one. So it's got a very short mean free path. But the farther apart the particles are, the greater the mean free path. Now, the mean free path, if you better read that section of the chapter, I hope you are. If you read that section, the mean free path ends up being greater than you might expect. And let me see if I can elaborate here. When I look at this crude picture that I just drew, let me get out a ruler here. To me, it seems pretty likely that if I just look at the distribution that I chose, it seems likely that this one is going to knock into another particle over a distance of something like 20 centimeters. I mean, by that time, it really should have hit another one. That's why I went ahead and drew another one over here. It's certainly not going to go like 5 meters without hitting one. That would be unlikely. But when you do the math, when you follow the steps laid out in the chapter, you actually do find that the mean free path for this silly example would be more than 20 centimeters. That's a little surprising. And it's because this picture is two-dimensional, but gases move in three-dimensional space. So imagine when this picture that I've drawn, imagine some of these particles being raised out of the page, some of them are raised into the page. So it might look like this one is going to strike that one, but it's very possible that this particle's up here and this particle's down below the page. So there's a little more room to move than you might be led to think by looking at a two-dimensional picture. Okay, well, what this problem is asking us to do is consider the ratio of the volume per atom. So first, let me make another silly picture. The volume per atom. I have to draw this two-dimensionally. I'm going to randomly draw a particle in each of these boxes. Now, they wouldn't actually be distributed this way, would they? Some of them would be in the same box. But this helps capture the idea. If you could measure the volume of one of these boxes, that would be the volume per particle. So the more spread out these particles are, the less dense they are, the greater the size of these boxes would be. Each of them would have an even larger box. It's like if I did something like this. And now I have to use a marker so you can distinguish these from the ones I've already drawn. Each of these has more volume per particle. They're moving around in a larger individual space than these are. So we're supposed to compare that volume, the volume available, the volume like belonging to each individual particle, compare that to the volume of the particle itself. Remember, we're going to think of these as hard spheres that have a definite diameter, d, which is 2 times the radius. Now, atoms are not actually hard spheres. They have more complicated structure than that, but we can think of them like that. And we're supposed to, again, given some other information, which I'll quote in a moment, we're supposed to compare the volume available per particle, available per particle to the volume of the particle itself. Okay, and that sounds really open-ended, and you might be thinking, where the heck am I supposed to start? It's a very trivial problem because we already have an equation relating these things. It may not look like it when you first glance at the equation, but you can massage the equation and get it to show that relationship. So what we're told here is that the mean free path is 10 times the atomic diameter. Oops, 10 times the atomic diameter. So the average distance that one of these particles can move before crashing into another one is about 10 times the diameter of the particle. So to me, this distance looks like more than 10 times the diameter. And that means, I'd have to redraw this, put them a little closer together. Well, the diameter is 2 times the radius. So we're really saying that the mean free path is 20 times the radius. What are we supposed to do with that? Well, if you go back into the chapter, I believe this was presented in the early part of the chapter, they just give us a formula for the mean free path in terms of some other things. So I'm just going to quote the result. Here it is, not something I have memorized. And your book actually shows where all of these quantities come from, with the exception of the root 2, because that requires some more sophisticated geometry. But the bulk of the derivation is in your book. It's kind of cool to see how it's done. And here we've got the number density. Hang on a second, I got to kill a bug. Capital N is the total number of particles, and V is the total volume. And the ratio of those two is called the number density times the square of the radius of the particle. There it is. Can we make sense out of this? Let's just look at each of these terms individually. R is in the denominator, which means if you make R bigger, lambda goes down. So the larger these, I'm just going to call them spheres, the larger these spheres are, the shorter the distance one of the spheres can travel before colliding into one of the other spheres, which makes perfect sense, right? Just think of like one of those bouncy ball pens. What do they call those? They used to have them at McDonald's, sometimes kids' birthday parties. Just imagine a bunch of those bouncing around in a room. The smaller those are, the farther they're going to be able to travel before they collide with each other. And you know what this reminds me of? This reminds me of in astronomy. You all know about galaxies. The Milky Way is this disc-shaped structure that has, 200 billion stars in it. And then over here, there's the Andromeda Galaxy. And they tell us that these two are on a collision course because of their mutual gravitational attraction. And billions of years from now, they're going to crash into each other. But then you read, it's actually possible for these to crash into each other without actually crashing, meaning they could just pass right through each other and never have a single collision between any pair of stars. Like there's a star here and a star here. Well, there's a bunch of stars. It's possible for these galaxies to pass through each other and never actually have a star from this galaxy crash into a star from this galaxy. And that's because so much of these galaxies is just empty space. Yeah, there's billions of stars, but they're separated by vast distances. So there's no need to actually have these stars collide with these stars. That's very strange. And that's kind of what we're talking about here. The smaller the stars are, in this case it's particles, the smaller they are, the farther they could travel within this body of particles without actually crashing into another one. And the other result here is also very sensible. The more particles you have per cubic meter, the shorter the mean free path. So the larger the spheres are and the more of them there are packed into any particular volume, the less far any given particle can go without crashing into another one. Okay, so that's the equation for the mean free path. You could almost memorize half of it by just remembering that relationship. And then the constants, of course, you'd have to look those up. Okay, so can we answer the question using this and the fact that the mean free path for this particular gas that we're talking about is 20 times the radius? We're supposed to find the volume per particle, right? That's this. So if you take, I've drawn 4 here. If you take the total volume and divide by the number of particles, well, total volume divided by 4 would be the volume per particle. That's what I've done here. take the total volume occupied by all the particles, divide by how many particles there are. That would be the volume roughly of one of these boxes. And compare that to the volume of each individual particle. In other words, the volume of these hard spheres. And that's 4/3 pi r cubed, where r is the radius of the particle. Okay, so really all we have to do is take this and rearrange some stuff. Can we do that? I believe so, because we may have an r squared here and we need an r cubed, but check it out. The book tells us that the mean free path is 20 times the radius of each particle. So let's rewrite this and say, well, 20r has to be 1 over 4 rad 2 pi n over v r squared. Okay, well, I'm interested in this ratio, so I'm just going to move some stuff around. N over v in the denominator, isn't that the same as v over n in the numerator? Okay, so let's see here. 20 equals v over n divided by, I've taken this r and put it downstairs on the other side. We still have the 4 rad 2 pi. There's our r cubed. Great, we're practically there. I'm going to take this rad 2 and put it over there. I've got a 4 pi r cubed. What I need is a 4/3 pi r cubed. So what I'll do is divide by 3 here. Well, what's that? That's a 1/3 in the denominator, which is like a 3 up top. So I've just multiplied the right side by 3. I need to also multiply the left side by 3 if this is going to be legit. So that here I've got 60 now, and I'll go ahead and take the root 2, stick it over there. This is 60 rad 2, and that's got to be volume per particle compared to the volume of the particle. That's the ratio that we wanted. Evidently, it's 60 rad 2, and I'm using your manual now. That's roughly 85. Okay, so the volume of each of these boxes would be something like 85 times the volume of each sphere. So this picture is not accurate if I wanted to illustrate this particular problem. I'd have to make the boxes much bigger. So that's kind of an abstract thing. Maybe you've never thought in those terms before. I certainly had not before studying this topic. But pretty remarkable that you can even calculate that stuff. And I do exhort you to remember, you can only carry this idea so far, because atoms are not really hard spheres. In fact, they're not even really like nuclei, hard nuclei with electrons buzzing around them. Depending on the way you probe the atom, it may behave kind of like a hard sphere, or it may behave like a wave, a standing wave inside this box. Very strange. You're going to have to read further into the book to learn about that. The Schrodinger equation, so-called wave mechanics. It's an awesome subject. I really wish we had 4 semesters to cover all the stuff, but then you'd be stuck at LBCC even longer, kind of like me. Next up is number 11. And since this video is just dedicated to problem solving, I'll be merely quoting results that were developed in your chapter. Again, it's really worth a read, 2 reads. You can't just read the stuff once and have it sink in. I'm still rereading it and retaining things that I hadn't retained before. But here is perhaps the most important idea to retain from this chapter, or to take away from this material. I don't want to say the most, because there's really a list of things that you must know, but this is on that list. It's a profound idea, and it's one that probably nobody was aware of before, let's say, the late 1800s. And I'm not an expert on the history of physics, but that's my understanding. Here it is. Let's think of this rubber ball here as a particle in an ideal gas. So this would be a monatomic gas. We know nitrogen would have 2 atoms stuck together in a nitrogen molecule. So this would be like neon or argon. And we say that this monatomic particle has 3 degrees of freedom. Yeah, I was going to say when it comes to translation, but that's really all it has. It can move this way. I'll call that the x-axis. It can move back and forth in this direction. That would be the y-axis. Or it could move back and forth in this direction. And that's the z-axis. Any arbitrary motion is just a combination of those three. That's it. So there are 3 degrees of freedom. And here's this profound idea that came out of thermodynamics in the late 19th century. This capital T here is the absolute temperature. We've already established that the higher the temperature, the faster those particles are zipping around. So as T goes up, the average kinetic energy of each of these particles goes up. You've still got some that might be moving around slowly until they get bumped by a fast-moving particle, and you still have some that are moving even faster than average because they got bumped particularly hard. But this is the average kinetic energy associated with each degree of freedom. 1/2 kT. Just want to memorize that. And what kind of sense can we make out of that? Well, we're talking about the average energy of a particle, and for a monatomic gas, an atom has practically, the mass is so inconsequential that if we're describing its kinetic energy in joules, we should be talking about a really small number. How many joules of kinetic energy can one atom have? Well, the answer is staring us in the face. Go away. Stupid thing rolls. It's staring us in the face because at room temperature, what is that, 20 degrees Celsius, add 273, round up. So at 300 kelvins, this would have to be 0.000000, something really, really small, so that the energy comes out appropriately in joules. And we already know that this is 1.38 times 10 to the negative 23rd. And that's how plugging in 300 Kelvin still yields an appropriately small number for the number of joules of kinetic energy that an atom has. And the units here would be joules per Kelvin, joules per Kelvin. Now, why do we even need this number? Before I get into that, let's talk about the 1/2 here. That comes from the equipartition theorem. Well, that's the average energy per degree of freedom. But this monatomic gas has 3 degrees. So it's got 1/2 kT of energy associated with motion along the x-axis, another 1/2 kT on average associated with y, and another 1/2 kT along the z-axis. So the total translational kinetic energy on average, your book uses this lowercase epsilon. The average total energy of a monatomic gas at temperature T would be 3/2 kT. And if you want to know why, if you need some justification for that, and I hope you do, read the chapter. So what we will be doing throughout this chapter is counting degrees of freedom. I wish I had another one of these to demonstrate. Yeah, I'll come back with that. But we're going to see that a diatomic gas, which has 2 particles, could also be rotating about 2 different axes. That adds 2 additional degrees of freedom. Let's think of these as the 2 atoms in nitrogen, for instance. If you get the temperature high enough, there's enough energy available to allow them to even oscillate. And then you can imagine a spring between them. They've got spring energy between them, and just the energy associated with the jiggling. That's another 2 degrees of freedom. So they could be doing this together. That's motion along the x-axis. They could be doing this together, motion along the y, motion along the z. There's 3 degrees of freedom for this molecule. Then there's an additional 2 for this. That's associated with the potential and kinetic energy of oscillation. And then they could be rotating like this, or what's the other one? Rotating like this. So it comes down often to just counting the number of degrees of freedom. But the so-called equipartition theorem from statistical mechanics tells us that for each degree of freedom, on average, each particle has this much energy at temperature T. So that's neat because we're tying together a macroscopic concept with this submicroscopic picture of tiny little atoms, the kinetic theory of gases. Everybody knows about temperature, everybody knows about thermometers, but not everybody knows that temperature is telling us, on average, the kinetic energy associated with the movement of these tiny particles that we can't see. You can't even see them under a microscope, at least not a visible light microscope. Okay, a word about the K here and the 1/2. the reason we have this K, it's bequeathed to us by the history of science. We chose to measure temperature in Celsius degrees. It made sense to choose a scale so that the temperature range from water freezing to water boiling, we chop that up into 100 pieces, and each of those pieces is called 1 degree Celsius or 1 Kelvin. That's convenient for everyday life. But if we chose a vastly different temperature scale, the K might not even be necessary. In fact, we're saying joules per Kelvin. The 1/2 could even be absorbed into the K. Yeah, I'm going to invent a different temperature scale right here so that you can understand what I'm talking about. Later, you can just dump this from your memory because you won't need it to solve problems. But let me just invent a new temperature scale using the fact that the average energy is 3/2 kT. Let's see here. Yeah, watch this. I'm going to call it a degree, just because that's one way of naming this this temperature scale. Instead of a degree, I'll go with a degree. 1 degree equals 2/3K kelvins. That's capital K for Kelvin. That's a lowercase k for Boltzmann's constant. Okay, this is a little silly, but let me go ahead and calculate that. 2 divided by 3 divided by 1.38 times 10 to the negative 23rd. Okay, so it's a huge temperature in kelvins. 10 to the 22nd. Okay, temperatures like that just don't exist on planet Earth, not by a long shot. I don't even think they exist at the center of the sun. But I chose this temperature scale because what you'll see here, what is the average energy of a monatomic gas particle at a temperature T equals 1 degree. I'm making this up, people. There is no such thing as a degree. Well, here it is. We know that a monatomic gas has 3 degrees of freedom, and there's a 1/2 kT quantity of energy per particle at temperature T. So we've got a total energy of 3/2 kT, 3 degrees of freedom. Well, that's 3/2 K times my temperature of 1 degree. But I just said that 1 degree was 2/3K kelvins. So 2/3K kelvins. And I'm not going to write the unit kelvins because I have not written joules per Kelvin, joules per Kelvin. Yeah, don't worry about the units too much here. Look at the numbers. See how the 2 cancels, the 3 cancels, the K cancels. And that would be an energy of 1 joule. Interesting. So if you actually had a gas that hot, it's unfathomable, but each individual gas particle would have 1 joule of energy. That's an insane amount of energy for something so small. I mean, just try to conceive of how fast that thing would have to be moving. I think you would find it would be moving faster than the speed of light if you use 1/2 mv squared. In fact, I'm certain, try it. Plug in a typical mass for a gas particle and find the necessary speed so that the energy comes out to be 1 joule. I think you're going to get a speed much in excess of 3 times 10 to the 8th. What's going on there? Well, it turns out that this is not the appropriate formula for kinetic energy at relativistic speeds. You'd have to use a different formula. That's another chapter we didn't have time to look at in this semester. That would be the chapter on relativity. Okay, so what I've done here is invent a temperature system or temperature scale so that 1 gas particle at a temperature of 1 degree would have 1 joule of energy. So in that temperature scale, and that's not the Kelvin scale, I can rewrite this equation. For the Kelvin scale, I have to have this 1/2 K out front, and K has a value of 1.38 times 10 to the negative 23rd. But on this scale, I could say this: the average temperature is, or excuse me, the average total energy per monatomic gas particle would just be T, where your temperature is in degrees. Silly example, but okay, if you had a quantity of gas at a temperature of 10 degrees, what's the average energy per particle? 10 joules. It's like the simplest possible equation. So I'm just trying to emphasize that don't be bogged down by the 1/2 K. You know, it seems like all this extra junk to memorize. It's just an artifact of our system of units, because we like to use the Kelvin scale to measure temperature, and we like to use joules for energy. I mean, heck, you could keep the Kelvin scale if you wanted, but then choose a different unit of energy and still make this equation look simpler. So it's not about the constants you see out front. I mean, those are important, but what you really want to know is basically temperature is the energy per particle. That is the essence of the equation. And that's not something that I understood when I first learned this. So I hope you get that, because that means you're ahead of where I was. Okay, so in order to solve number 11 now, because that's what this is about, let's see, let me just write down what they tell us. We're talking about a quantity of neon gas. We're told that the number density of particles, how many particles per cubic meter, is a whopping 5 with 25 zeros after it. Remember, number is not, it doesn't have a dimension, so it's just inverse cubic meters. We're also told that the atoms are moving with an RMS speed. Let me add, this is for neon, an RMS speed, root mean square speed of 660 meters per second. And I'd like to point out at this time that your solutions manual has some serious typos in it, which is one reason I'm doing this problem. So sorry about the typos. Now, VRMS, what is that all about? VRMS, that is the square root of the average value of the square of the speed. Whoa, remember, you've got a mole. Well, for a typical macroscopic quantity of gas, you may have a mole of particles. They've all got different speeds. I mean, how could any two have the exact same speed? Like, how do you even measure that, first of all? And even if you could, are any two particles really going to have the same speed out to like 20 decimal places? That's impossible. So they have all different speeds. But what you could do is first calculate all of their squared speeds, theoretically. Find all their squared speeds, then take the average of that, and then take the square root. And that's basically the average speed. It's not the same as average speed, but those numbers are close together usually. Sorry, V average. For various reasons, this is a more convenient quantity to use in theoretical calculations. Okay, now how are we supposed to relate these two? Well, the first thing we should keep in mind is the average energy of these particles. Well, that would be the average of 1/2 mv squared. Remember, the total translational kinetic energy of a monatomic gas would just be 1/2 mv squared, but we're looking for the average value of that. And here's the crucial connection. Look right here. The VRMS is the square root of the average value of the square of the speed. So if I want to get rid of the square root sign, I'd have to square VRMS. Now, when you average a quantity like this, since the mass of the particle doesn't change, every atom of neon's got the same mass, you can take the constants and pull them out before you do the averaging. So this would really be 1/2 m times the average of v squared, but the average of the squared speed of all these particles is by definition VRMS squared. So we can write that as 1/2 m VRMS squared. Okay. I'm going to put a box around this to emphasize it, because that is worth memorizing. If you're talking about monatomic gases, all of their energy is associated with translation. We're not talking about a diatomic dumbbell type molecule that can also rotate or vibrate. We're just talking about kinetic energy of translation. And we know from mechanics that that's 1/2 mv squared. So this is one way of expressing the average kinetic energy of a bunch of monatomic gas particles. But we also have this other relation that I was just discussing. The average energy is proportional to the temperature. And in the Kelvin scale, we go with the 3/2 kT if we want to express epsilon in joules. So we also have this relation. Epsilon average is 3/2 kT. So I think it'll help you. It'll help you navigate this chapter to just memorize both of these. These are two different ways of expressing the average energy per particle, the average kinetic energy per monatomic gas particle. Because we're going to see that if it's diatomic and you also take into account the rotation, you would have 5/2 here. So let's not worry about that now. Try to memorize these both. And then I will go further with that. Let's go back to the ideal gas law, which ties together a lot of this stuff. We know that for an ideal gas, this should be true. Well, there's another way of writing PV equals nRT that I haven't talked about a lot yet. I call this the Pervenert law, but it doesn't sound like Pervenert if you write in terms of not the number of moles, but the number of particles. Remember, number of moles would be the total number of particles divided by the number of particles per mole. Right? This would convert from total particles into number of moles. But then we can recognize that if you take the gas constant and divide by Avogadro's number, that is Boltzmann's constant. Your book always puts that little b there. I don't care about that. This is 8.31. When you divide by 10 to the 23rd, positive 10 to the 23rd, excuse me, 10 to the positive 23rd, you get a 10 to the negative 23rd here. That should help you remember this relationship. So R over NA, that is K. So the other way to write the ideal gas law would be NKT. Same equation. This is the molar version, and this is in terms of the total number of particles. You should really know both of them. So here is how I connect these two. It helps me cope with memorizing everything because I'm not actually necessarily memorizing everything. This NKT looks an awful lot like 3/2 KT. So let's do this. PV is equal to, I'm going to stick in the factor of 3/2 that I'd like to be there. So I'll pay for it with the 2/3 out front. There's a 2/3 N times 3/2 KT. See what I did there? I inserted the 3/2, paid for it with the 2/3, because now I recognize this is the average kinetic energy per particle. Let me also move the V over here. So I've got pressure equals 2/3 times number density times, and if this is the average kinetic energy per particle, we could also express it in terms of the RMS speed. So I could just substitute 1/2 mv RMS squared, because this is the same as that. And now I can answer part B of the problem. I guess I'm doing part B before I do part A. Part A, they're asking for the temperature. We can go back and do that. How do we calculate the pressure? Well, this was given. They just told us how many particles there are per cubic meter. And they also gave us the RMS speed. Now for the mass, you'd have to look that up. The mass for neon. Well, neon is atomic number 20 from the periodic table. So there are 20 nucleons. That's probably 10 protons and 10 neutrons. 20 nucleons per atom, and each nucleon has a mass of something like 1.66 times 10 to the negative 27th kilograms. I know I'm running out of space here. So what would that be? 1.66, 10 to the negative 27 times 20. Okay, 3.32 E negative 26 kilograms. So now we know how much mass each atom of neon has. We know the number density and we know the RMS speed. We can just plug all that stuff in and find the pressure within this gas. So I'm going to do that real quick. 2 divided by 3 times 5 times 10 to the 25th times 1/2 times that tiny mass. Lastly, times the RMS speed, 660 squared. And I find that's the pressure here. Let me put that into kilopascals. So 241,000 pascals would be 241 kPa. And you know what? I got a different number in my notes here, so let me check this real quick. Okay, nope, I'm still getting the same answer here. I'm looking more carefully at the solutions manual versus the problem written at the back of the chapter, and they goofed some of the numbers. I think there's just some confusion over which numbers were used, so hopefully you don't have that problem in mastering. But at least that's a reasonable number, right? 101 kPa is atmospheric pressure. Now they'd like to know the temperature. Well, one way to do that would be to go back to this form of the ideal gas law and solve for T, because now we know P. Yeah, check it out. We could say temperature. If I solve this for temperature, I get temperature is equal to pressure over K times N over V, where that's the number density. So we could just plug everything in and evaluate the temperature that way. Your book does it a different way, and I think it's worth looking at. There's another equation that they use often. And again, you don't even have to memorize it because it comes from this. These are two different but equally valid expressions for the average kinetic energy of a monatomic gas. So all we have to do is do this. We could say, or 1/2 mv RMS squared is the same as 3/2 kT. We could solve that for VRMS. That's what they like to do. VRMS is, well, we'd have to move the 2 over. That would cancel this 2, divide by m. You've got a 3 kT over m square rooted. And that is a handy formula. That shows up often. 3 kT over m, that's lowercase k. So if you know how massive a particle is and how hot the gas is, you can immediately calculate how fast they're zipping around. I don't have that memorized. Well, I sort of do, but I don't need to memorize it because I know these two results, and I can combine those very quickly to relate the speed to the temperature. Now, in this case, they're asking for the temperature, so we could invert that. Let's see, square both sides again and move some stuff around. Maybe you can check my algebra here. I'm going to square both sides, solve for T, and I would find that's m VRMS squared over 3K. Okay. And I'm looking at your solutions manual. Okay, that's not how they're doing it. They chose to use PV equals NKT, which was my first suggestion. But let's check the results here. Take the 3.32 times 10 to the negative 26 times 660 meters per second squared. Your solutions manual goofed that number. Divided by 3, divided by Boltzmann's constant. You know, Boltzmann was one of the early proponents of the atomic theory of matter. He was really sure that matter consisted of atoms. And he was pushing that idea in the late 1800s. Okay, fine, I'll hit equals. He was pushing that idea, and it didn't gain much traction in the physics community. This was, you know, near the turn of the 19th, 20th century. And I think that contributed to some depression he was experiencing. And he was on holiday with his family somewhere in Europe, killed himself. And then like a year later, within just a couple of years, everybody was on board. Oh yeah, atoms, totally. Matter is made of atoms. Should have stuck around just a little bit longer. In fact, he really was, that really is unfortunate because 1905 was just around the corner and all those, you know, the bombs that Einstein dropped on the physics community. But hey, maybe if Boltzmann had still been around, he would have been taking up space, so to speak, in that community. Maybe Einstein would not have done what he did had things been different, you know? So what's the point in speculating? But I find that the temperature is 349 kelvins, and your book came up with a different number because your book makes mistakes. They keep goofing numbers. The important thing is that you know how to manipulate, excuse me. The important thing is that you know how to manipulate the equations. Okay, there's one last thing worth looking at in this equation. Really, I can just start with PV equals NKT. I meant to say this in the last chapter, chapter 19. If you solve for the pressure, you get this simple result. This is another way to write the ideal gas law, and it makes so much sense. It says if you double the number density of particles but keep the temperature constant, you'll double the pressure. Of course you do, right? Because think back to that FET simulation with all the little gas particles bouncing around inside that volume. If you've got twice as many particles in that volume, they're going to collide with the walls twice as often. That's twice the pressure. And if you increase the temperature, they're all zipping around faster. They collide with the walls with greater force. Again, greater pressure. So this relationship, which was somewhat intuitive prior to the kinetic theory of gases, and Boyle's law, Charles' law, people had some intuition about how if you heat up a gas, you would expect it to have greater pressure. But it makes even more sense when you can relate it to these little tiny particles that we can't see. We take our ideas from mechanics, force, kinetic energy, pressure, and we apply those to this vast number of teensy-weensy particles, and we were able to recover a macroscopic result. I mean, think about how cool that is. I hope you read through the derivation. PV equals nRT was known well before people accepted the existence of atoms. I don't know how early in the 1800s, maybe even before. I don't know exactly when the ideal gas law appeared, but it was definitely before people accepted that gases consisted of atoms. So to be able to recover the ideal gas law by starting from first principles, by applying Newton's laws to these tiny little particles that you can't see, that's really satisfying. Last thing I'll add to that, for those of you who are interested, those of you who may go on and study more physics, I saw the derivation of the ideal gas law from the kinetic theory of gases many years ago. But in my own reading in the last year or two, I saw the same equation derived starting from quantum principles. So you can also consider a quantity of gas particles as a whole bunch of standing waves, and that's a very different starting point. You can apply the laws of, or the theory of quantum mechanics to those standing waves and still recover the ideal gas law. So that was really sobering, because it's like these are two totally different starting points, and I'm still arriving at the same equation. So there's some truth there in nature that we're getting at. Now that we've had that discussion, we can easily knock out a couple of trivial homework problems. They don't seem so mysterious now that we've recognized that there are two equivalent ways of expressing the average kinetic energy per particle in a gas. Here's one way to calculate it. And remember, this came from just averaging 1/2 mv squared. When you take the average of 1/2 mv squared, you turn that v squared into vrms squared. That should be the same as 3/2 kT. The equipartition theorem tells us that there's 1/2 kT of energy associated with each degree of freedom. And we're talking about, well, truthfully, we're talking about diatomic molecules here. And I mentioned just previously that they could have additional degrees of freedom, but we're not supposed to worry about that yet. In fact, I don't think your book has even introduced that at this point in the chapter. So hold on to that thought. For now, we'll just talk about 3 degrees of freedom. And we can move the 2 over, well, basically solve this for T. This is where that relationship came from. That was the, okay. I just realized that I was answering a slightly different question from what the book is asking. Hold on to that. Here's what they're asking. At what temperature do hydrogen molecules, that's a hydrogen stuck to a hydrogen, at what temperature are they moving at the same average speed, basically? Remember, VRMS is not quite the same as average speed, but close enough. Same VRMS as N2 molecules at 100 degrees Celsius. Okay. We can do this with math. We can do it with the equations, fine. But it seems easier. It won't seem so mysterious if you think about it physically. Remember, temperature is a measure of the average kinetic energy per particle, irrespective of which particle you're talking about. So if you've got a quantity of enormous, I don't know how to, let's see, because it's called the ideal gas law, but you could imagine an ideal gas of extremely massive particles that actually aren't gas particles. I don't know, pick the heaviest gas you could think of, fluorine. I'm assuming that's a heavy gas. At 100 degrees Celsius, those fluorine particles have the same average kinetic energy as teensy-weensy little hydrogen molecules at the same temperature. So it's the energy that's the same for a given temperature. Now, because a hydrogen atom is so much less massive than fluorine, for instance, it's going to have to move faster to have the same energy. Think of a golf cart and a semi-truck. If you've got a golf cart and a semi-truck moving down a road with the same energy, doesn't the golf cart have to be going a lot faster because of its reduced mass? So it's the energies that are the same at a given temperature. Now, here they're asking something different. They're saying it's not the energies that are the same, it's the RMS speeds that are the same. So consider this. If both the hydrogen and the nitrogen were at 100 degrees Celsius, we're told that the nitrogen is at 100, but if they were both at 100 degrees Celsius, by my prior reasoning, wouldn't the hydrogen molecules have to be going way faster than the nitrogen molecules so that they have the same energy? And that means if they have the same speed, then the hydrogen's got to be a lot colder. So we're already expecting that the temperature for hydrogen would have to be much lower so that the hydrogen particles are going at the same speed as nitrogen. Now, if you don't follow that, it's okay, because the equation will tell us. Let's solve for the quantity that's the same here. So I'm going to solve for VRMS. Again, you've already seen the formula. You could just take it from your book, but it's nice to see where it comes from. For an ideal gas, this is the RMS speed in terms of temperature and mass. So this is what's the same. This quantity is some particular value for hydrogen, and it's the same value for nitrogen. So what we can do is set them equal to each other. So the temperature of the hydrogen, mass of the hydrogen over here, this is the RMS speed, and we're told that it's the same as the RMS speed for the nitrogen, temperature of the nitrogen, mass of the nitrogen. And remember, you can only use this equation if your temperatures are expressed in kelvins, or really they have to be absolute temperatures. You could have a different scale, but it would still need to be a scale on which 0 is absolute 0. And then, of course, on that different scale, K would take a different value as well. All right, what can we get rid of here? The 3 and the K, don't need it. They divide out. Let's square both sides, and we would have this. Temperature of hydrogen over mass of hydrogen, temperature of nitrogen over mass of nitrogen. Simple ratios here. And we're interested in the necessary temperature for the hydrogen. So the temperature of the hydrogen would be, see that? It's the reciprocal ratio. Because hydrogen is so much less massive than nitrogen, this is a ratio less than 1. That means the hydrogen gas would have to be colder than the nitrogen gas. Now, do we need to find the mass of each particle in kilograms? Of course not, because you'd have the same conversion factor on top and bottom. Let's just look at the ratio of their atomic mass numbers. In other words, the number of nucleons. Well, hydrogen, the atom only has a single proton and no neutron. By the way, did you know that? It's just a proton and an electron. Sometimes hydrogen will have an extra neutron, so that doesn't change its chemical identity, and then that's called deuterium. Deuterium, because I think deuter has something to do with 2. And if you have water made with this kind of hydrogen, H2O, if the 2 hydrogens have a neutron That's called heavy water because it really would be significantly heavier. How cool is that? I don't know if it's radioactive or what, but imagine if your body was composed. Wow, I never thought of that. If all the water in your body was made from deuterium, or if the hydrogens were deuterium, your body would be significantly heavier. What would that make you, like a super fighter? You know, you just punch somebody and they go flying. I don't know how that works. There's the next superhero idea. And check it out, we've already got their name. The Deuter. Okay, I take credit for that, right? This video is time-stamped, okay? I'll take you to court if you steal that idea. Okay, so since there's two hydrogens, there are two nucleons. Nitrogen is atomic number 7 on the periodic table. So each atom has 7 protons, 7 neutrons, that's 14, but there's 2 of them, so it's 28. I believe I did this right. And then we're told that the temperature of the nitrogen is 100 degrees Celsius. Don't forget to convert, add 273, so 373 kelvins. How hot or how warm would this hydrogen need to be? .6 kelvins. That's way down there. That's close to absolute zero. Now I will subtract 273 to get the temperature in degrees Celsius. Okay, wow. So even near absolute zero, hydrogen molecules are so much less massive that even at that temperature, they're moving as fast as nitrogen molecules would be moving at what we call boiling temperature. Okay, so it's a little surprising, but simple problem once we have that formula. Last one for the evening, number 18. We're told that a quantity of molecules has an we must be talking about a gas here, that's got an RMS speed of 600 in SI units. And then we're told that the pressure gets cut in half and the volume gets cut in half. So what's the new VRMS? Can we reason through this with common sense first? Well, our common sense, you know, after having acquired some of this knowledge here, our base of common sense is a little different than the average person off the streets. But here's the idea. There's no mention of any change in temperature. So if you cut the volume in half, but the temperature is the same, didn't you just squeeze the same number of particles into a smaller space, but they're still moving as fast as they were before? Wouldn't you expect the pressure to go up? Think about that. If you've got a bunch of particles here, I just drew 5 of them, and they're all zipping around at a particular speed. So that's described by the length of these arrows. And then you cram them into a smaller box, but they're still moving as fast as they were before. Wouldn't they be bouncing around a lot more times per second than they were here? In other words, the pressure would go up. If you kept the temperature the same and decreased the volume, the pressure would tend to go up. And yet they're telling us that the pressure went down. It was cut in half. So the only way for that to happen is if the temperature also decreased. Does that make sense? Let's see, I could write it P equals nRT over V. If you cut the volume in half, but don't change the temperature, you've got a 1/2 down here, that means a 2 up top. Cutting the volume in half would double the pressure. And yet they're telling us that the pressure is 1/2 of what it was before. So can you see what's going on here? If I had a factor of 1/2 here, and I want a factor of 1/2 here as well, I would have to have a factor of 1/4 here. So you bring the 2 up, 2 over 4 is 1/2. So the temperature's got to go down by a factor of 4 in order for this to happen. And let's see, we know that VRMS is proportional to temperature, because I'm using that same relation that I keep going back to, this one right here. Kinetic energy, kinetic energy. Okay, so if we need the temperature to go down to 1/4 of its original value, do you see that the RMS speed would have to go down to 1/2 of its original value? Because 1/2 squared is 1/4. Cool. I just reasoned through this without actually doing any math. The new RMS speed would have to be 300 meters per second. But let's do this a little more formally. Yeah, but not that much more formally. I'll go with PV equals NKT, which I can write as 2/3 N. What was I doing here? 2/3. I'm having a Joe Biden moment here. 2/3 N times 3/2 KT. That's why I chose to do that, right? Because then I can replace this with 1/2 M VRMS squared. I did this on purpose because I recognize that 3/2 KT is the same. These are two equivalent expressions for the average kinetic energy per particle. I hope that at this point you're irritated with me for repeating this so many times, because if you are, that means that you've learned it and you got it. I'd rather have you irritated with me than, oh, I don't know, desperate because you're not ready for your exam here. Okay. What are we trying to do here? If the pressure is cut in half and the volume is cut in half, what happened to the RMS speed? So I'm really using proportional reasoning once again, just in a different way. So cut in half, cut in half. In other words, you need a factor of 1/4 here. Same thing would have to happen over here. This would also have to be cut down by 1/4, and that means each individual factor of VRMS would have to be cut down by a factor of 1/2. Okay, so VRMS new would be 1/2 of the original VRMS. 1/2 of 600 is 300. How can we do this without just using the proportional reasoning? Here's that last way you could do it. I'll pick up with this starting point, the 1/3 N MVRMS. In this problem, pressure is changing, volume is changing, VRMS is changing. What's not changing is the mass of the particle and how many particles we've got. So you can use that technique where you put everything that changes on one side and everything that doesn't change on the other side. And that leaves us with PV over VRMS squared would have to be NM over 3, and that's a constant. So this ratio doesn't change, and that means the pressure initial, volume initial over VRMS squared initial would have to be equal to pressure final, volume final over VRMS squared final. Pardon me. So let's move some stuff around. VRMS squared final, I'm moving this over here. That would be pressure final over pressure initial times volume final over volume initial times VRMS squared initial. A lot of algebra here. And finally, we can take the square root of both sides. VRMS equals the square root. And once we've taken the square root, this just becomes the original VRMS of 600. And I'm going to go ahead and plug in the ratios. Remember, they told us that we've cut the pressure in half. So the final pressure is 1/2 P initial. 1/2 P initial over P initial is 1/2, right? You can just recognize that we're talking about a ratio of 1/2. 1/2, same thing for the volume. What's the square root of 1/2 squared? That would be 1/2. Okay. So that's the formal way I can think of for doing this. Probably the safer way to do it, right? If you had something like that on an exam. I'm not going to give you this problem. I'm just saying, show as much work as you can. Okay, that's enough for tonight. Till next time.